Okay, so I would like to thank the organizers for giving me the opportunity to present the result of this long-term study on silicate dust analogue. So it's a study that was done with many colleagues from Arab, from Moscow, and from IAS, and some more from Toulouse and Lille for the experimental part. They are cited in the presentation. Alors.
C'est quand j'avais de moi à chaque fois.
Clique dessus, ouais. C'est quand il y a un truc qui apparaît, en fait, c'est ça. So the outline of my talk is the following. I will present briefly the motivation that started this work, present you the experimental measurements, the derivation of the optical constant, and I will compare them with cosmic dust model that are commonly used in the community. So the motivation was dust emission in the ISM and in the cosmic, in the cold ISM, sorry, because cold dust is a very good tracer of the interstellar medium. It is used to derive interstellar cloud mass and to study star formation, for only quoting a few reasons. So dust emission in the diffuse ISM is presented here. So you have the emission of diffuse ISM from the near infrared up to 1 millimeter. And it is adjusted with a model, a cosmic dust model, in this case, the Compiègne dust model. And the adjustment is made with the DustM model, emission model. So, alors, est-ce que je reclique? Yes, so with this spectral energy distribution, we are used to, I will present you the different dust components that are included in cosmic dust model. So here you have the pH component responsible for the, or proposed to be responsible for the mid-infrared emission band. Then, à chaque fois, il faut que je reclique? D'accord. Then you have the population of very small grain, which are not very well constrained, that emit here around 40, 60 micron. And then you have this peak here due to large grains, cold grains in the far infrared and 2 millimeter, which here in this Compiègne model is produced by a population of large amorphous carbon grains and large amorphous silicate grains. So the Compiègne model is one that uses two different composition of component of large grain, but in many models you have only one component of large grain, and these are silicates. So how do we model dust in the far infrared? Well, it's rather simple if you make several assumptions. That your grain are in thermal equilibrium with the radiation field, that your medium is optically thin, and that you don't have any temperature gradient along the line of sight. Then you can relate the signal to the mass of the dust. Let's go directly here. The opacity of the dust, the black body at the temperature of equilibrium of the dust, and the distance of your cloud or of your object. And in the far infrared, you can express this kappa, which is the opacity or the mass absorption coefficient, simply as a power law of the wavelengths with a value here of reference that you take at a certain wavelength, and beta, the spectral emissivity index. Alors, il faut que je recommence. Tac. Which is taken to be compressed between in the range 1 from 2, independent on the temperature, independent of the wavelength. And just a small short note to say that the opacity and the spectral index that you derive from the observation are averaged on all the dust components that are on your line of sight and on your cosmic dust model. But several observational facts were in contradiction with this simple modeling in the far infrared. Just to cite few of them, you have the beta, the anti-correlation of the spectral emissivity index with the temperature. So this is a study made on many different cold cores. And you can see that the spectral index vary with the temperature, and that in addition, you can derive two different spectral index if you use only the Herschel data or if you use only the Planck data. So beta seems to be dependent on the wavelengths as well as the temperature. Oh, it's complicated. And so you have also the far infrared submillimeter axis here. Where you can see that it's not possible to reproduce the observation with a single black body. You need to add another dust component, which has a different temperature and also a different spectral emissivity index. So in fact, the model we have and we adopt is not able to reproduce this observation. So several propositions were made to explain this observation and this discrepancy between observation and modeling. For example, it could be due to mixing of dust population in the line of sight. It could be due to noise in your data or to temperature mixing in the line of sight or to bias from the fitting method. Or it could also be a true behavior of your dust grains, and it could be related to the intrinsic properties of the grain with the temperature. And so we wanted to investigate this proposition. So what about lab data? Lab data already exists when we started this study. And well, most of the measurements were done at room temperature and only for short wavelengths. Some showed, some studies were performed at varying temperature and long wavelengths, and they already showed that the opacity was varying with the temperature and the wavelengths. And so the opacity and thus the spectral index. So what is used in cosmic dust model? Well, here I just list some of the existing cosmic dust model that you can use in your modelization. There are many more, but you have basically the models that reproduce the diffuse ISM and those that reproduce the dense ISM. And so the aim of this model is to provide absorption and scattering cross-section or opacity, usually for spherical grains. Only a very few and the most recent model consider spheroidal grains, and they can also be used to calculate polarization cross-section. And the silicate component that they have is based either on experimental data that were measured at room temperature, or they were constructed to reproduce the observation, and they are in any case extrapolated at long wavelengths. So there was a need to make a kind of systematic study of new dust analogues to explore this variation of the opacity, both with the temperature and the frequency. So this is what we did with a team of people here that participate to the production of the dust analog, to their characterization, etc. And so we studied amorphous silicate sample of varying compositions, some containing only magnesium and some containing also iron. We have a submicronic grain population. Here you have the size distribution. Here you have some electron microscope images that you can see the size and the shape. And we measured the mass absorption coefficient from 5 micron up to 1 millimeter, maybe sometime less depending on the sample, from 10K to 300K on the SPAR setup at IRAP and on the L beamline at Soleil. So here, just an example of 4 different samples in the mid-far infrared, where you have the 2 vibrational bands of the silicates, and the full mass absorption coefficient we measured from 5 micron up to 1 millimeter. In blue, you have the opacity. Well, you have the mass absorption coefficient at 10K, where you can derive in the far infrared the spectral emissivity, which is the slope of the emissivity of the MAC, and you have it also at 300K. So you can see readily that the MAC is the mass absorption coefficient is varying with the temperature. It also varies with the frequency. It was seen also in previous studies. And you can note that we have different behavior for the different sample. So this is due to the fact that these effects here are related to the amorphous nature of the sample. And each amorphous sample, we have a different amorphous structure. So it's not completely a surprise that we see that. So we checked that for other samples, we checked that if we average over different samples, we still see the trends of this varying mass absorption coefficient with both the temperature and the wavelengths. Okay, the results now. So it was not enough to have the mass absorption coefficient for this data to be used in astronomical models, because what you need is to model the cross-section of your favorite grain in terms of grain size, of grain shape, of inclusion, core mantles, and aggregates. So for that, you need the optical calculation. So we calculated them using Kramers-Kronig relations. So you have some of, well, here you have the Kramers-Kronig relation. And we have to make some assumption for this. So we have to give a value of the refractive index in the visible because we did not measure it. We have to choose a grain size. So we decided to work in the Rayleigh limit because our grains are relatively small compared to the wavelengths, which is very true in the far infrared and less true in the mid infrared. And we had to assume a specific grain shape to make this calculation. So here you are. You have the optical constant, here the refractive index and the absorption coefficient in the measured spectral range at the various temperature that we measured. We also provide extrapolated optical constant, because to use them in a cosmic dust model, you need to have the data on the whole, the largest spectral range, and we did not measure it everywhere. So in the UV and near infrared, I took data from the literature that were measured on similar samples, but not the same samples. And in the millimeter, I just used a power law. And then we also provide interpolation at any temperature in case you need to calculate your mass absorption coefficient at 128 Kelvin, for example, instead of the 100 Kelvin that we measured. So we decided to provide for each of the sample a way to interpolate it properly, and we check the consistency of this interpolation within the Kramers-Kronig relation. So we did some error estimation on the optical constant. I will go very quickly on that. So on each of the parameters that we had to choose to do the modeling, so we have errors. We checked an additional possibility that we absolutely do not control in our experiment, is the possibility that the grains are agglomerated into the pellets. And we find that it was not a big problem. So we sum all these error and we end up with optical constant with error bars that allows us to check that, well, still the behavior we observed are really clear. So then we can compare with a cosmic dust model, and here the optical constants that are used in the TEMIS model and the astrosilicate model from Drain in color. So you see well, differences, especially in the far infrared and here in the mid infrared. Here, this huge difference is due to the fact that in the TEMIS grains, you have some iron, whereas you don't have them in the sample we measured. So then you can calculate the opacity for example, a prolate grain with a certain axis ratio. So here in colors, you have the opacity calculated with the silicate from the optical, from the cosmic dust model, sorry, and those calculated for each of our magnesium-rich samples. So you have a wide diversity. So what you can do is average all these different composition and structure. It's not, I think it's quite relevant for ISM studies. And here you have in red the average of 4 samples, and in orange the average on 3 samples. So what you can see is that the sample we measured and the optical constant we derived gives mass absorption coefficient that are higher at 100 micron, but also at 1 millimeter. And so these modeled grain will be more emissive. So I think, yes, okay, it's the same. We have the same with the iron-rich containing silicate. And okay, just an advertisement that this data will be used in the new version of the TEMIS model that will use a mixture of several magnesium-rich silicate samples for non-spherical grain. So that will be a huge improvement in cosmic dust model. So here, just the comparison of, in black, the actual TEMIS opacity, or here it's the efficiency, absorption efficiency, and the new data in color. So the grain will be more emissive in the far infrared. This is just for the conclusion. All these data are available here at this Stop CODA databases, which is hosted by SHADE, which is an infrastructure that was developed by Bernard Schmidt in Grenoble. And well, I recommend you that you go to this SHADE portal. You have a lot of data on solid states. Well, you have a lot of solid state data, let's say.